Welcome all. Today we will explore the classification of powertrains used in electric vehicles. A powertrain refers to the set of components that convert stored energy into mechanical power at the wheels. In EVs, depending on how the motor, battery, engine, if present, generator, and transmission interact, we get different powertrain architectures. Understanding these classifications is crucial because the performance, efficiency, cost, and complexity of the vehicle depend heavily on the powertrain chosen. In an electric vehicle, the fundamental powertrain consists of a battery pack supplying DC power, an inverter converting that DC into AC, an electric motor generating torque, a transmission or reduction gear, and the wheels that receive this torque. This is the pure electric layout. However, in hybrids, we also include an internal combustion engine and a generator. Based on how these components share or split responsibility, we classify EV powertrains into different categories. Major classification of EVs based on powertrain are battery electric vehicle, hybrid electric vehicles, series hybrid, parallel hybrid, series parallel, power split hybrid, thirdly plug-in hybrid electric vehicles, and then the fuel cell electric vehicles. Major classification of EVs powertrain based on motor layout are single motor, dual motor, AWD, and the in-wheel motors. A BEV is the simplest and most efficient electric powertrain where there is no engine at all. The battery stores electrical energy, the inverter feeds the motor, and the motor drives the wheels through a single-speed reduction gear. Examples include the Tesla Model 3, Tata Nexon EV, and Nissan Leaf. In a series hybrid, the engine is never connected to the wheels. It simply powers a generator. The motor is the only device that creates wheel torque. This gives excellent low-speed torque and smooth driving, but the system has conversion losses because power flows through generator, battery, and motor. Example vehicles are Nissan e-Power Series hybrids and BMW i3 Rex. A parallel hybrid allows both the engine and the electric motor to deliver torque to the wheels together or independently. Here, the engine is connected to the wheels through a transmission, and the electric motor is also mechanically linked to the wheels. Both can work together, which means the engine helps during cruising, and the motor helps during acceleration. This improves efficiency but requires complex clutches and transmissions. Example vehicles are Honda Insight Hybrid and Hyundai Ioniq Hybrid. Series parallel hybrids are the most advanced. They combine both architectures using a planetary gear set. Depending on driving conditions, the vehicle can behave like a series hybrid or a parallel hybrid. This gives excellent fuel economy, especially in city traffic, but the system is mechanically and electronically complex. Example vehicles are Toyota Prius and Toyota Camry Hybrid. A series parallel hybrid uses a power split device, usually a planetary gear set, which allows the engine's power to be split between generator, engine, and wheels. Technically, many PSDs are planetary gear sets. The three nodes are often called sun, planet carrier, and ring. Any one of those can be the engine input, any can be the generator, and any can go to the wheels depending on design. The planetary gear set allows the engine's power to be split between the mechanical path, which connects power directly to the wheels, and the electrical path, which connects power to the generator, then to the battery, the motor, and the wheels. By varying that split, the vehicle can run like a series hybrid, a parallel hybrid, or any blend between them. Think of the PSD as a three-way junction that enforces a mechanical relationship between three shafts. Call them A, B, and C. Because of that relationship, power delivered into the PSD can be divided between two outgoing paths automatically. Some power can go straight through mechanically to the wheels, and some can be routed into the generator. By changing the generator speed, torque, you change how much power goes which way. If the generator resists rotation, acting like a load, then more engine power flows into electrical generation. If the generator is allowed to spin freely, more engine power flows mechanically to the wheels. The PSD, therefore, makes it possible to control engine speed independently of wheel speed to some extent, and that is the key control advantage. Now let's talk about the series mode where the electrical path is dominant. In this mode, the engine drives the generator through the PSD to produce electricity. Then the electricity goes to the battery or directly to the traction motor. Finally, the traction motor drives the wheels. Energy flow in this mode is from the engine to generator, generator to battery, battery to motor, and finally from motor to the wheels. We use them under low vehicle speeds, stop and go driving, or when the control strategy wants the engine to run at a very efficient steady point. Now let's talk about the parallel mode where the mechanical path is dominant. In this mode, the engine provides torque mechanically through the PSD to the wheels. The electric motor assists or is idle. Energy flow in this mode is from the engine to PSD and PSD to wheels. The optional path to assist is from the battery to motor and motor to wheels. The optional path is provided for the electric motors so that they may add extra torque for acceleration. We use them under high load or highway cruising where mechanical connection is most efficient. Now let's talk about the series parallel mode, which is the blended or power split mode where both paths are used. Engine power is split, which means a part goes mechanically to the wheels and a part drives the generator to charge the battery or feed motor. The traction motor may provide additional torque. Energy flow in this mode is from the engine to PSD and PSD to wheels, which is the first path, and the second path is from the engine to PSD, PSD to the generator, generator to the battery, battery to the motor, and motor to the wheels. We use them when we need to optimize the fuel consumption across a wide range of speeds loads. Finally, let's talk about the regenerative braking. In this mode, the wheels drive the motor, and the motor acts as a generator and sends energy back to the battery through the PSD. Energy flow in this mode is from the wheels to motor, which now acts as a generator, and then from the generator to the battery. This recovers kinetic energy that would be lost in friction braking. We will now discuss on what the Electronics Control Unit, ECU, tries to do in an EV. It formulates the control goals and strategies through a well-defined protocol. The objectives of the ECU are to minimize fuel consumption for a given driving demand, to respect battery SOC and keep it inside the safe window of charging or discharging as required, to meet the driver torque request quickly and smoothly, to protect component through the constraints like max current, temperatures, and mechanical limits. Common strategies include the rule-based control, where if the speed is less than X, then run in EV in series mode, else run the EV in parallel mode. Secondly, the optimization-based control, where the equivalent consumption minimization strategy, ECMS, and predictive control are performed when route or speed information is available. Plug-in hybrids are essentially hybrids with big batteries. You can charge them through the grid like a BEV, and they can run purely on electricity for 40 to 80 kilometers before the engine turns on. This is useful when full electric range is limited or charging infrastructure is sparse. Example of such EV are the Toyota Prius Prime and MG Hector PEV. In a fuel cell electric vehicle, hydrogen is stored in tanks and fed into a fuel cell. The fuel cell generates electricity to run the motor and charge a small battery. These vehicles are emission-free at the tailpipe but require hydrogen infrastructure. Example of such EV are the Toyota Mirai and Hyundai Nexo. We will walk through the step-by-step operation of a PEM fuel cell, beginning with a single cell and then scaling up to a full stack, while focusing on key elements such as hydrogen, oxygen, platinum, sulfonic acid groups, electrons, protons, water, and heat. Hydrogen is supplied to the anode flow channels, and air bringing oxygen is supplied to the cathode, ensuring both gases reach their electrodes. At the anode, hydrogen meets the catalyst and splits into protons and electrons. The protons move across the hydrated PM, which only allows H to pass, while the electrons are forced through the external circuit and generate useful electrical power. With the cathode, oxygen combines with those electrons and the incoming protons to form water, plus heat that must be removed by a cooling system. And because one cell only gives about 0.7 volts, we connect many cells in series for voltage and in parallel for current to build a practical fuel cell stack. At the anode, the process starts with platinum. Its surface absorbs hydrogen molecules and weakens the HH bond, making it easy for hydrogen to split. That oxidation step produces two protons and two electrons, so now we have H ions and free electrons. The protons naturally migrate across the membrane toward a lower electrochemical potential, but electrons can't cross it. They're forced through the external circuit, and that flow of electrons through the load is the electric current we use our usable power from the fuel cell. Now let's look at the membrane itself. The PEM is a polymer. Naphthalene is the common example, and it contains fixed sulfonic acid groups. These groups attract and stabilize protons and help create water-based pathways for proton movement. The actual transport happens through what we call the Grothus mechanism, where protons don't drift slowly through the membrane, they rapidly hop from one water molecule to the next, almost like passing a baton along a relay. On the cathode side, oxygen from air arrives and meets three things at the catalyst surface: the protons that have crossed the PEM, the electrons returning through the external circuit, and the platinum catalyst that helps drive the reaction. Here, a reduction reaction takes place. Oxygen gains electrons and combines with the protons. If you write it for a single oxygen atom, you get the half reaction, and for a full O2 molecule, you get the complete cathode reaction. The end product at the cathode is water, sometimes liquid, sometimes vapor, along with heat released during the reaction. Under ideal thermodynamic conditions, a hydrogen-oxygen cell should give about 1.23 volts based on Gibbs free energy. In reality, the voltage is lower because we lose performance to activation over potential at the electrodes, ohmic resistance through the membrane and contacts, and mass transport limits at high current. A polarization curve shows this clearly. At low current, activation dominates. In the mid-range, ohmic losses set the slope, and at high current, mass transport limitations pull the voltage down. So a practical cell usually operates around 0.6 to 0.7 volts. That's why a vehicle stack aiming for roughly 300 volts needs on the order of 400 plus cells in series. In BEVs, the placement of motors also classifies the powertrain. Some cars use a single motor, while high-performance EVs use two motors, one for the front and one for the rear axle. In-wheel motors go even further, and they remove the transmission entirely and put the motor directly inside the wheel hub. The simplest EV layout is the single-motor powertrain, where one motor drives either the front or rear axle through a reduction gearbox and differential. It's inexpensive, efficient, and perfect for everyday city driving. A step up from that is the dual motor setup, with one motor on each axle, creating an all-wheel drive EV. There's no mechanical link between axles, so software can manage torque independently for better traction and acceleration. Beyond that, performance and off-road EVs may use multi-motor systems, sometimes one motor per wheel. These four-motor or in-wheel systems remove gearboxes and differentials and allow extremely precise torque control, improving stability and cornering. Axle-mounted motors remain common, while in-wheel motors trade impressive control for added unsprung mass, which can affect ride comfort. We can also classify EVs by which wheels get the driving force. If the motor drives the front wheels, it's a front-wheel drive EV, which is common in budget models because it's cheap and offers good traction. If power goes to the rear wheels, it becomes rear-wheel drive, which performance EVs prefer for better acceleration and handling. And when motors power both axles, we get all-wheel drive, where software can shift torque instantly for far better control and stability than mechanical AWD systems. We can also classify EV powertrains by the transmission. Because electric motors work efficiently over a wide speed range, most EVs use a single-speed reduction gear, simple, compact, and low maintenance. But some high-performance models, like the Porsche Taycan, use a two-speed gearbox to combine strong acceleration with a high top speed, and heavy commercial EVs may adopt multi-speed units for efficiency under varying loads. So, based on transmission, we have single-speed and multi-speed EV powertrains, each serving different performance needs. Another way to classify EV powertrains is by electrical system voltage. Early EVs used 400-volt architecture, which is fine for regular fast charging and most passenger cars. Newer high-performance models are moving to 800-volt systems, which lower current, boost efficiency, and enable ultra-fast charging, sometimes adding a couple hundred kilometers in just minutes. Heavy-duty trucks may even move toward 1,200-volt systems. So we now talk about 400-volt, 800-volt, and emerging 1,200-volt powertrains. EV powertrains can be classified in multiple ways: by energy source, by motor layout, by wheel drive configuration, by transmission, and by voltage architecture. Each classification gives us clarity about the vehicle's purpose, performance, cost, and technology level. Understanding these classifications helps engineers choose the right powertrain architecture for specific applications in passenger cars, commercial vehicles, high-performance cars, and even off-road vehicles. In the next session, we will explore EV component nomenclature and how to read specifications of motors, batteries, inverters, and drivelines. Think about starting from a traffic signal. A BEV gives instant torque. A series hybrid moves first on the motor while the engine comes in later to recharge. A parallel hybrid may use both motor and engine, and power split hybrids start smoothly on the motor and blend in the engine when needed. At highway speeds, BEVs stay efficient. Series hybrids lose some efficiency. Parallel hybrids cruise very efficiently on the engine, and power split systems use the engine mechanically while the motor fine-tunes the ratio. During braking, BEVs and series hybrids regenerate strongly. Parallel hybrids do less if the clutch is open, and power split hybrids recover energy with smart control. Each architecture has trade-offs. BEVs are mechanically simple but need a large battery. Series hybrids make wheel drive simple but lose efficiency in energy conversion. Parallel hybrids are very efficient on the highway but introduce mechanical complexity. And power split hybrids try to blend the best of both worlds, but they're costly and require sophisticated control algorithms. So to wrap up, EVs can be classified by how energy reaches the wheels, giving us BEVs, various hybrid architectures, plug-in hybrids, and fuel cell vehicles. BEVs themselves can be arranged as single motor, dual motor, or even in wheel systems. When we compare how these layouts behave during launch, cruising, and regenerative braking, we see why manufacturers pick different powertrains based on cost, efficiency, and performance targets. Thanks for listening. We'll continue with more EV powertrain topics in the next lecture.